Hello. Okay, so now we're going to talk about chemical shift and how it relates to shielding. All right, so methanol, why not? So we're starting with a molecule in an external electric field, external magnetic field. And so one of the things that NMR is going to measure is the local magnetic field. Okay, so there's going to be a different local magnetic field at this proton than at this proton, okay? And so depending on the specific nuclei and the electron distribution around those nuclei, they will affect, or their B local or their local magnetic field will be different depending on their chemical environment. All right, so this B, so B is smaller at the nucleus if the electron shields the nucleus. Okay, so the greater shielding you have, the smaller this B local is going to be. And one of the ways you can think about that is if this external magnetic field is, so if there's no electrons whatsoever, if it's just a nucleus, then the nucleus will feel that external magnetic field. However, if you have electrons with their own magnetic angular momentum component spin, then they are going to align in the direction of this B0, and they're going to then reduce the overall magnetic field felt at this nucleus. Go team. So basically you can think of it as how you have spin up and spin down, and so the net spin is 0. So that same effect would happen with the more electrons that you have around the nucleus. So for the magnetic field to affect the nucleus, it must overcome, so for this to have any sort of effect on that nucleus, it must overcome that loss of magnetic field due to the electrons. So that is going to be our delta B, which is the small additional field that's going to be basically added to what's happening at B local, and that's going to be minus sigma times B0, where this is called the shielding constant. And so the small additional field that you've got is equal to this minus shielding constant times B0. And so this is what we're going to focus on and relate to the chemical shift. Okay, so local B is equal to B0 plus delta B. So again, this is that additional field that arises from the electrons. And then we're going to just input that into here. B0 plus a minus sigma B0 equals B0 times 1 minus sigma. Okay, go team. So now what we can do is take a step back for a second. Remember that this whole thing originates from energy B equals 0. There's degenerate states. As soon as you have the external magnetic field not equal to 0, the nuclear spins are going to have this delta E separation. And that Larmor frequency is going to be related to that energy separation. Okay, so now what we want to do is we want to put this in terms of the Larmor frequency, which means that the Larmor frequency is proportional then to the gyromagnetic ratio B local divided by 2 pi, but that's just equal to, now we put this in, 1 minus sigma B0 gamma 2 pi. Sweet. And the cool thing about this is, so now we have our Larmor frequency in terms of B0 we control. That's just the strength of the magnetic field in the big ass magnet. That's our gyromagnetic ratio. So depending on what nuclei we have, that's just a number, an experimental value that we can look up. 2 pi, thank goodness, not changing. So now this shielding constant, that's going to be what we use to identify which nuclear environment do we have? Do we have one with a lot of deshielding? So this all, the oxygen is pulling electron density away from this hydrogen, so you don't have the same shielding as you do for this hydrogen. So this one's going to have less shield. Yeah, this one's going to be less shielded. This one's going to be more shielded. Okay, so this one's going to have a smaller value here. This one's going to have a greater value here. Cool. Okay. I'm going to pause and erase. Okay, so if you think about this picture, when you have no magnetic field, now if you have a slightly different magnetic field due to shielding, due to a bunch of electrons being around this hydrogen and fewer electrons being around this hydrogen, what you're going to do is you're going to slightly adjust this. And I'm talking slight. It is so teeny tiny, the difference is ridiculously teeny tiny. But if you have, oh, found the red marker. So here might be the other delta E equals H nu lambda, or Larmor frequency. So this Larmor frequency might respond to that proton, and the purple Larmor frequency might respond to that proton. So now we can start to get a chemical signal, or sorry, a resonance signal that tells me that this one is different than this one, which is part of the point of NMR. You know, we want to be able to identify these different nuclei. And we're doing that by identifying the different chemical environments or nuclear environments. Okay, but this spread is dependent on B0. So if you have a weak magnetic field, this won't be very separated. If you have a strong magnetic field, i.e. like 10 to 20 Tesla, it's going to be much bigger. So what we want to do now is figure out, well, what standard are we going to measure everything with respect to? In comes tetramethylsilane. So TMS, tetramethylsilane. So silicon, CH3, CH3. Okay. So each of these protons are going to have, so they're all the same. So all same nuclear environment. And they all are perfectly shielded. And actually, I'm going to take that ideally. Go back to an ideal gas idea. So they're ideally shielded, okay? So you've got electronegativity is very similar between carbon and hydrogen. Electronegativity is very similar between carbon and silicon. There's not that much difference. So the electrons are nicely, what is nicely? Their distribution is pretty symmetric. Okay. Because of that, we want to know then what is the Larmor frequency of all of these protons of tetramethylsilane, or TMS. So what we're going to do is we're going to measure everything with respect to this frequency. So if I have, and just to make things clear, so purple is now TMS. Now I've got, so here's my frequency of my, say, I've got CHH2R groups. So I want to know that nuclei. So that one, I'm going to say, all right, that minus my standard divided by then my standard. Okay, so this is essentially a percent difference from the standard. So okay, so it's a percent difference from the standard. The kicker though is that this is so teeny tiny. Like, so TMS is, say, the purple line, and then now I've got my blue line. It is so small that this is typically on the order of I forgot the micro, so 10 to the minus 6. So typically on order of 10 to the minus 6. So it's really small. So what we do is we say, okay, well, I want to know times 10 to the 6th to put this into a value that's somewhat reasonable. And so because of that, this is essentially a parts per million. Go team. Well, that's nice. So then I'm going to basically say that this whole thing is what my chemical shift is. It's the shift with respect to the Larmor frequency standard of TMS of my new frequency of my new nuclear environment times 10 to the 6, and that puts it in units of parts per million. So this is equal to the chemical shift, and it's in ppm. It's a unitless value because it's a percent difference. Okay. If you have any questions on that, pause, email. The next thing I want to talk about, so if you want to know the chemical shift of TMS, that would just be, well, nu 0 minus nu 0. I'm just going to stop there because this whole thing would equal 0. So the chemical shift of TMS is going to be 0, and we measure everything with respect to that upfield, downfield. All right, I'm going to pause, erase, and I'm going to give you some numbers of different chemical shifts, and we'll talk a little bit more about how to interpret those. Okay, so the chemical shift of TMS, 0, related to the frequency of your nuclei in choice, or of choice, minus what the frequency is of TMS. So here we've got, for proton, the chemical shift of the hydrogens on a methyl group, CH3, 0.8 to 1.2, for CH2, 1.1 to 1.5, and for the hydroxyl group, 2 to 5. So you can see that it gets much higher the more electronegative, or the more withdrawing the electron, or the more withdrawn the electrons are from the proton. So you can think about this. So you've got more electron withdrawing, or in all honesty, what you do have, you have the coefficients of this being much higher. In all honesty, that's what you've got. But because you've got much more electrons here, the electron density is pulled away from the hydrogen, which causes this B local to be closer to B0, okay? Whereas for a CH3 group, so that proton, you're going to have B local be farther. Oops. You're going to have B, oh, that's right, sorry. B local will be more different than B0. And so, whereas this B local is much closer to the standard, so it's closer, so a smaller chemical shift. But in this case, it will have a larger shielding constant. So there's an inverse proportionality between that. The shielding constant is going to be much greater, but then it's going to be a smaller chemical shift because B local is has a greater difference than the B applied. Go team. So that's something important to think about. So this goes up, this goes down. Go team. So your shielding constant increases, your chemical shift is going to decrease. Okay, other things of note, then I want to talk about our general trends of the chemical shift, which are what? This is kind of cool. So this is measured, okay, and that's going to equal several types of shielding, all right? So you're going to have the shielding of the local, and this is the electrons from the nucleus. Then you're going to add that to the shielding from the neighbor, because remember, you've got a big sample with all of these are all little magnetic moments, spin nuclei, or nuclei spin. You're taking an average of all of those. So you are going to have some shielding due to the nearest neighbor that's next to you. And most of this is in the liquid state. So you've got really close proximity. We don't really do gas phase NMR. And so you've got close proximity. So the shielding due to the neighbor on the target nuclei. And this is from the electrons in the atom on the molecule. So I just lied to you right there. I was saying it's from the other. So this would be intra. And then here we go. This is the inter. So this is of the solvent. And this is the electrons from neighboring molecules. Sorry about that. So this is the electrons within the same molecule. So that would be like if you had CH2OH, oops, CH3OH, then this proton and then these three protons would affect one another's chemical shift through the shielding constant. And then if you had a bunch of methanols in the same liquid state, then the next, so methanol 1 might affect methanol 2, and that would be from the shielding constant of the solvent. Okay,